Hello and welcome to INDIANTOPIA. I'm your host Angela Navarro and we are here to discuss about relations and functions. For starters, we will be discussing about relations and its subtopics, rules of membership and in a relation, and properties of a relation. The next one would be functions and the operations on the functions.
For our first topic, relations!
Hello everyone, today I will discuss to you about relations. What is a relation? It can be thought as a table that lists the relations of elements to other elements. Abstractly, we define a relation to be the set of ordered pairs such that we consider the element of the first ordered pair to be related to the elements of the second ordered pair. This is a good example of relations. It is an example of a thesis, which is made up of members and roles. Member number 1 is John, second is RJ, Chunsi, and then Sweetzen. On their roles states project manager, programmer, business analyst, and database administrator. John is related to project management. RJ is related to programming, Chunsi is related to business analytics, and Sweetzen is related to database administrators. The intersection of the truth and the belief circle is considered as the knowledge, meaning the relationship of both resulted in knowledge. A relationship, in conclusion, is the result of the intersection of two sets, such as the finite set of truth and the finite set of belief.
For our next topic, rules of membership in relation.
Rules of membership in the relation. Relations may be defined by given rules for membership by satisfying a given condition. This means that a number can be a member of a relation if it follows a certain rule. And here are some examples of the rules of membership in the relation. Rule number 1, the divides evenly condition. The relation R is defined by the rule the ordered pair x and y is a member of R if x divides y evenly or has a zero remainder. For example, we have set x with members 2, 3, 4, and 5, and set y with 10, 11, 12, and 13. Our R is equal to the ordered pairs 2, 10, 2, 12, 3, 12, 4, 12, and 5, 10, which we can all see that the members of our relation satisfy our condition that x divides y evenly or has a zero remainder. Like 10 is divisible by 2, 12 is divisible by 2, 12 is divisible by 3, 12 is divisible by 4, and 10 is divisible by 5. The other members of set x and y is not a member of the relation because they do not divide evenly and has a remainder. Like 11 divided by 2 is equal to 5 with remainder 1. Now, the domain of our set is 2, 3, 4, 5, and the range is 10 and 12. Rule number 2, the less than or equal to condition. The relation R is defined by the rule the ordered pair x and y is a member of R if x is less than or equal to y. For example, we have set x with 2, 4, 6, and 8. We will have R is equal to the ordered pairs 2, 4, 2, 6, 2, 8, 4, 6, 4, 8, 6, 8, and 8, 8. We can see that 2 is less than 4, 2 is less than 6, 2 is less than 8, 4 is less than 6, 4 is less than 8, 6 is less than 8, and 8 is equal to 8, which satisfies our condition that x should be less than or equal to y. So the domain and the range of this set is 2, 4, 6, and 8.
For our third topic, properties.
Properties of relation. Reflexive. A relation R on a set V is reflexive if whenever small v is an element of large V. Then, quantity V, V is an element of R. A relation R on a set V is not reflexive if there exists some small v is an element of large V such that quantity V, V is not an element of R. Consider the set of my family members F. The relation has the same age as on F is reflexive because every person in the set has the same age as himself or herself. Here are the examples. In this example, you can see that this is reflexive because each values in the quantity are equal to each other because they have the same age as each other. Irreflexive. A relation R on a set V is irreflexive, not to be confused with not reflexive. If for every element small v is an element of large V, it follows that quantity V, V is not an element of R. A relation is not irreflexive if there exists some V is an element of large V, such that quantity small v, small v is an element of R. An example for an irreflexive relation on the set of my family members would be is a parent of, because a person can be a parent of himself or herself. The members of this relation are quantity Mila, Itzik, quantity Mila, Miki, quantity Mila, Ina, quantity Gabi, Itzik, quantity Gabi, Miki, quantity Gabi, Ina. As we can see, in this relation, it cannot be reflexive because they cannot be equal to one another. Because, as said earlier, a parent cannot be the person himself. Symmetric. A relation R on a set V is symmetric if whenever quantity R1, R2 is an element of R. Then quantity R2, R1 is also an element of R. A relation is not symmetric if there exists some quantity R1, R2 is an element of R, such that quantity R2, R1 is not an element of R. In the set of my family members, the relation is a sibling of is symmetric. Why? Because that said relation is reciprocated, meaning if one person is your sibling, then that person has you as their sibling as well. It is reciprocated. Asymmetric. A relation R on a set V is asymmetric if for every quantity R1, R2 is a member of R, where R1 is not equal to R2, it follows that R2, R1 is not an element of R. An example of an asymmetric relation on the set of my family members is a parent of, as described earlier. This is because person 1 is a parent of person 2, but person 2 cannot be a parent of person 1. Transitive. A relation R on a set V is transitive if whenever quantity AB is an element of R and quantity BC is an element of R. It follows that quantity AC is also an element of R. Given R is equal to quantity AB such that A and B are an element of Z and quantity A minus B is divisible by K. Let A and B as an element of R and B and C also an element of R. Then A and B are element of R and B and C are element of R.
As a given, a minus b is divisible by k. Therefore, b minus c should also be divisible by k. From this, we can conclude that a minus b plus b minus c is also divisible by k. And we can get from that information that a minus c is divisible by k. Therefore, a comma c is an element of R. Equivalence relation. An equivalence relation is a relation that is reflexive, symmetric, and transitive. If the relation has all three properties, you can report that it's an equivalence relation. Let variables m, e, a as positive integers. A relation R is defined on the set Z by A relation B if and only if A minus B is divisible by M for A and B as an element of Z. Show that R is an equivalence relation on set Z. First, let A an element of Z. Then A minus A is equal to 0, which is divisible by M. Therefore, A relation A holds for all A is an element of Z. Hence, R is reflexive. Let A and B an element of Z, and A relation B holds. Then A minus B is divisible by M, and therefore B minus A is also divisible by M. Thus, A relation B logically implies B relation A. Hence, R is symmetric. 3. Let A, B, C as an element of set Z, and A relation B and B relation C both hold. Then A minus B is divisible by M, and B minus C is also divisible by M. Therefore, A minus B equals to quantity A minus B plus quantity B minus C is also divisible by M. Thus, A relation B and B relation C logically implies A relation C. Therefore, R is transitive. Since R is reflexive, symmetric, and transitive, so R is an equivalence relation on set Z.
For our fourth topic, functions.
Function. What is a function? Function is a special kind of relation. It is a relationship within two different sets of numbers or variables. It is also called mapping. A function essentially maps a number in one set to another set. A function is defined as a relationship f from A to B where A and B are two non-empty sets, such that for every element of A, there's a unique element of B. It is important to keep in mind that a function maps a value 1 and only 1. Two values in one set could only map one value, but one value must never map two values because it is called a relation, not a function. Meaning a relation of one to many is not accepted. Type of function. Our first type of function is one-to-one or injective function, where f of A to B is said to be one-on-one or injective function if element of A there's a different element of B. It shows in example number 1 that each element has a corresponding element B. And in example 2, each element A there's a corresponding element B, but it doesn't really require that every element A should point every element in the set B. Our second type of function is onto or surjective function. A function f A to B is said to be onto or surjective function if every element of y in set B there is an element of x in set A such that f of x is equals to y. So in example number 1, we could see that every element of A has a unique and corresponding element in B. So in our second example, we can see that every element in A is pointing every element in C, even if there's two values in A that points a one corresponding value in B, which we could say that is a many-to-one type of function. Our last type of function is a bijective function. It is a function wherein one-to-one and onto function is combined. Both properties are shown in the example below. We can see that all elements in A are connected to B, respective one-to-one of each element of A to a different types of element on corresponding values of set B.
For our last topic, operation on functions.
Now, we are going to tackle about operations on functions together with some examples. Operations on functions are similar to operations on numbers. Each operation has a format definition that produces a new function, where each function is defined for all x in the domains of both function f and function g. So here are the formulas on how to get the sum, difference, product, and quotient of two formulas. Aside from these operations, another way of combining functions is the composite functions, which is denoted by f of g of x, where x must be in the domain of g of x and g of x must be in the domain of f of x. To solve the composite function f of g of x, substitute the value of g of x to the function, then solve for f of x by substituting the value of x. Here are some examples on how to do operations on functions. The first problem would be find the f of g of x and g of f of x for the functions f of x is equals to x plus 3 and g of x is equals to x minus 2. Find also the sum, difference, product, and quotient of f of x and g of x. In order to solve for f of g of x and g of f of x, we need to use the formula for composite functions. In solving f of g of x, we are just going to substitute the value of g of x into f of x. To solve for g of f of x, we are just going to substitute the value of f of x to g of x. For the next part of the problem, we need to use the four basic function operations in order to solve it. In order to get the sum of f of x plus g of x, we are just going to substitute its values, and it will result to x plus 3 plus x minus 2. When you add x plus 3 plus x minus 2, the answer would be 2x plus 1. To solve for the difference of f of x minus g of x, we are just going to substitute its values, and it will result to x plus 3 minus x plus 2. And the answer for x plus 3 minus x plus 2 would be 5. To solve for the product of f of x times g of x, we are just going to substitute its values, and it will result to x plus 3 times x minus 2. X plus 3 times x minus 2 is equals to x squared plus x minus 6. To solve for the quotient of f of x divided by g of x, we are just going to substitute its values. It will result to x plus 3 divided by x minus 2, where x should not be equal to 2. Problem number 2. Find the f of g of x and g of f of x for the functions f of x is equals to x plus 2 and g of x is equals to x squared. Find also the sum, difference, product, and quotient of f of x and g of x. We just need to do the same thing to solve for this problem. Use the formula for composite functions to solve for f of g of x and g of f of x, and then use the four basic function operations for the rest.
Thank you for tuning in to Indiantopia. I hope that you learned a lot of lessons. Bye!